You run a query on a table with 100 million rows. It comes back in 2 milliseconds. Here's the strange part. It did not read 100 million rows. It read about 4 pages off the disk, and it found your answer. The thing that makes that possible is the index, and almost every index you've used is a B tree. Let's see why. Start with no index. You ask for one row. Where is it? The database has no idea, so it checks every row. Row 1, row 2, all 100 million. That's a full table scan. Order N. Fine for 1,000 rows. Fatal for 100 million. We need to find a row without looking at all of them. You might think, just keep the rows sorted and binary search. Cut the search in half every step. That's order log n. 2 problems. Insert one new row into a sorted array, and you have to shift everything after. And here's the one that really matters. Databases live on disk. Disk doesn't hand you one row. It hands you a whole page, a block of data at once. So the cost that counts isn't comparisons. It's how many pages you pull off the disk. The real goal is simple. Find the row in a few page reads as possible. The goal is what a B tree is built for. Picture a tree, but not a binary tree with 2 children per node. Each node in a B tree is one disk page, and it's packed with keys, dozens, hundreds. Each key points you to the next page down. So instead of splitting the search in 2 at each step, you split it into hundreds. The tree gets very wide and very shallow. Let's put numbers on it. Say each page holds 100 keys. 1 level points to 100 places. 2 levels, 10,000. 3 levels, 1,000,000. 4 levels, 100 million. So any row in a 100 million row table is 4 page reads away. There's your 2 milliseconds. Now compare to a plain binary tree. 2 children per node. To index 100 million rows, it needs about 27 levels, 27 page reads versus 4. Same data, same log n idea. The whole win is packing many keys into one page. So the tree stays short. Short tree, fewer disk reads. And because the leaves stay sorted and linked, scanning on a range is cheap too. So the B tree isn't complicated. It's one idea pushed hard. Make the tree as wide as a disk page allows, so it stays as shallow as possible. You trade a little more work on writes and a little space for reads that stay fast, no matter how big the table. Next question. What happens when 1,000 people write to that table at the same moment without tripping over each other? That's MVCC, and it's a beautiful trick. I'll show you.